This video is about applications of trigonometry of right triangles. As always, begin by reading carefully through the textbook and taking some good notes, but then secondly, consider the following highlights. We'll recall that we've already discussed something called trigonometric ratios, and we're going to need these. So this would be what we called SOHCAHTOA. In a previous topic, this is just an acronym that reminds us that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. So those letters in that order spell SOHCAHTOA, which is of course not a real word, but it helps us remember those things. Now, secondly, we're going to add some things to this. So we'll work or talk about solving a right triangle, and what it means to solve a right triangle is to find all angles and side lengths. So if we're working with a given triangle, we want to find all the angle measures of it, which would be at most 3, of course, and then all the side lengths of it. In addition, let's add some other definitions that we'll need in some of our applications. The first of those is called the angle of elevation. And to understand what this angle means, or this definition means, we're going to use a bit of a diagram, which will include simply a horizontal line. So we have drawn a horizontal line on our page, and then on one side, or it's actually a line segment because it ends on each side, but on one side of that line segment, I'm going to draw a little stick figure person because this is typically known as the line of sight. That's, from the point of view of a person. And if the line of sight, in other words, the person looking, is gazing in a way that is upward when compared to the horizontal, flat line sight, and if that angle measure is shown by perhaps rotating, if you imagine looking horizontally but then kind of moving your head upward to gaze, let's say, like up into the sky, then that direction of going upward from the horizontal is what you would call an angle of elevation. So we could label that angle theta, which is simply in that spot illustrating the angle of elevation. And then secondly, there's something called the angle of depression. Now, thankfully, this is not depression as in sadness. This is the depression as in a direction. So if we take the same picture, that is a horizontal line segment, and we also imagine a little person or a stick figure on one side of it, and this time, instead of gazing, imagine looking straight across on the horizontal, but then if you gaze downward, so maybe you're standing atop a cliff or a balcony, and you move your gaze or kind of turn your head downward to look below the horizontal measure or the horizon, then that angle that would be rotating downward to that new line of sight would be the angle of depression. So those little phrases or words, when understood, will help us, I think, understand some of the word problems, and then maybe diagrams we'll have to draw in order to work with them. All right, I'm going to change the color of our angle of depression here, just so we keep these organized visually as well. But there they are, angle of elevation and angle of depression. Now let's get into some examples where we'll start to use and probably accomplish some of these things. The first one is going to say this: solve the right triangle. Well, as we just understood or noted, to solve a triangle means to find all of its angle measures and all of its side lengths. Now, we're given a diagram for this problem, and I'm going to describe that now. It's a triangle that's a right triangle, as known by the right angle being labeled with a little box or square in the corner of it. And then on the side length across from that, of course, that's the hypotenuse. I'm going to call that C just because I have to give it a name, and we've used C, I think, in the past for a hypotenuse. You could call it anything, but we know the hypotenuse is always across from the right angle. And then the side that would be adjacent to the right angle, or in other words, touching it on one side, has a length of 35 that's given. Now, we don't know what the units are of that. Maybe 35 feet, meters, miles, we don't know. Doesn't really matter though for now. We just have a label there. And then the angle that is between the hypotenuse and that given side length of 35, so in other words, the angle that's kind of squished between or meeting where those meet, that angle is given as 52 degrees. And then the side that's across from the 52 degrees, which is one of the legs of this triangle, is just unknown. It's not labeled with anything, so we don't know it. Now, if our point is to solve a right triangle, of course, we're going to have to find it. So I'm going to give it a name just for convenience here. I'm going to call it A. And that's just because I want to be able to find that, and it's more helpful, I think, in algebra to give it a variable name so we can do some math with it. Now, let's talk first about some angles here, right? Because we, to solve this triangle, have to find all the angle measures and all the side length measures. Well, we know two of the angles already, don't we? The right angle is of course, or obviously 90 degrees. And then the other angle, or one of the other angles that's given, is 52 degrees. So thankfully, we can use some facts about triangles to get this other missing angle, which I'm going to give a name. I'm just going to call it theta, again, because we'll then be able to find it easily. But what we know is that the angles inside a triangle must add to 180 degrees. Well, if you already have 90 degrees for your right triangle, right angle, that means the other two together must then add to another 90 degrees, because altogether they have to add to 180 inside total. So if we already have 90 for the right angle, and then the other two must add to 90, that would be the total of 180. So what that tells us is that theta, the other angle we don't know but we're trying to find, plus 52 degrees, or 52, you could just label it, that's the other given angle. Those together must be 90 degrees, as mentioned. What that means is, by algebra, I could simply subtract 52 from both sides of this equation that started as theta plus 52 equals 90. So the 52s will cancel. This is just equation solving like we're used to with algebra. And of course, this leaves us with theta being 90 minus 52, which is 38. Now, all of these are in degrees for these angles, so I'm going to mark that as 38 degrees. And in fact, we probably should mark the 90 as 90 degrees and the 52 as 52 degrees all the way throughout, because we're really working with degrees, so let's just be clear about that. Which means, okay, our angle theta, the one missing angle, or the one angle we did not know at the beginning of this problem, is 38 degrees. All right, so with that being known, we know all the angle measures inside this triangle. Now, you can go in the diagram and actually label that angle if you'd like, or write it in as 38 degrees. Now that we've found it, that's fine. We have to indicate that somewhere, somehow. All right, that means all we have to do next is find the side lengths, and we're given one of them, as mentioned already, that's 35. We have two other side lengths to know or figure out. That would be the hypotenuse, labeled C, or the other leg, that's not the 35, that's labeled A. Now, in order to find those, we have to use some kind of trigonometric ratio that we already know. And we can just kind of recall the SOHCAHTOA for that. We know the angle 38 and we know the angle 52, and really we could use either one of those in order to put together a trigonometric ratio. For example, if we take the 52 degree angle that was given already in the diagram, then we know the side adjacent to it, which was labeled 35. So if I want to find one of the missing sides, like I'll just look across from the angle 52, or I find the side length A, or what I've labeled A, we know we can find or use a trigonometric ratio that involves both the side that we know, which is the 35, and the side we want to know, which is the A. Now, in relation to the angle 52, remember, this is what's important, is labeling these correctly. The 35 would be the adjacent side, so I'm going to label that adjacent, and the side across from 52 labeled A would be the opposite side, which means we're looking for a trig ratio that involves both the adjacent and the opposite. So scan through your SOHCAHTOA and you'll find that it's tangent. So we can say tangent of our angle, which of course is 52 degrees, equals, as we know, opposite, that's A, over adjacent, which is 35. And so all of a sudden we have an equation with one variable, that is the letter A, that I just used to put in there. You could label it X, it doesn't really matter which variable name you use, but we have to find that side length. So what I can do to solve for A, of course, is multiply both sides by 35, which is just some algebra here. The 35's on the side we were just using with A over 35. The 35, when multiplied there, would cancel with the 35 in the denominator, leaving us only with A on that side all by itself. That's a good sign. That's good news. On the other side of the equation, that leaves us with 35 times the tangent of 52 degrees, which is something we can find on our calculator, thankfully. All right, let's go ahead and take out our TI-84 Plus graphing calculator and see if we can just compute this 35 tangent of 52 degrees for our side length A. In order to do this correctly on the calculator, you have to make sure you're in the right mode, right? So you're using degrees in this problem, and we're either using degrees or radians, and there is a mode in the calculator that needs to match that. So we're going to press the mode button, kind of in the upper left corner of the calculator here. It says mode. When we do, we'll notice a menu of options. If you go down, it looks like about the third line, there's an option that says radian, and then next to it, it says degree. Usually by default, the radian is selected, so we need to move over to degree and then hit the enter key to shift into that mode. Once we're in it, that mode, we can quit this menu by hitting just second and then the mode button to quit. But that put the calculator in degree mode, which we need since we're using degrees as our angle input. So now I'm simply going to type what we see in our equation, which is 35, and then tangent is the tan button, T-A-N, and then I want 52, where it'll assume we mean degrees because we put it in degree mode. So we have 35 tan 52, just like that. I'm going to hit enter. Let's see what happens. It spits out a number, which can indicate, as you can maybe assume here, that it's assuming you mean there's 35 times the tangent of 52. You don't even have to put a little star for multiplication between there. You could, but you don't need to. The calculator will assume you mean multiplication. All right, so the value it gives has many decimal places. Of course, it's 44.79795713. So we can just round that. This problem may not have specified what to round. If it problem does, then of course follow those instructions. When in doubt, round to 100th, so 2 decimal places, which means we'll round this to 44.80, just to round it to 2 decimal places. And I'm going to go ahead and write that in here. So A is approximately 44.8 or 44.80 if you're rounding to 2 decimal places. Now remember, we don't know the units of the side lengths, so we don't know what to call that. Could be feet, could be meters. We'll just leave it as an empty unit for now, since that's how the problem was given. But that is the side length of A, which is one of our missing side lengths that we needed to find. All right, so I'm going to box that in because that's one of the things we had to end up with. The only thing left then, so A is done, theta is done. The only thing left for us would be to find the side length C, which is our hypotenuse labeled. Now, once you get the side length we just found as A, you could use the Pythagorean theorem, since you know 2 sides on a right triangle and are trying to find the third side. That would be a valid way also to figure that third side out. But I'm just going to use a trig ratio because I think they're nice and simple once you have what you need in a triangle, which is, you know, an angle and all the sides labeled. And furthermore, I'm going to use a non-rounded side length. Okay, so notice they gave us 35 originally as one of the side lengths, and that was just a clean whole number 35. The side we just found, we rounded to 44.80. So I'm not going to use a rounded side to find another missing side. It'll just create compounding error. Rather, I'm going to use the given non-rounded side of 35, which means I'm going to use the adjacent. I'll even reuse the angle 52, but you could use the 38-degree angle as well and get the same result. But I'm going to reuse 52 since we're already kind of warmed up with it, and we've already labeled the adjacent side of 35 next to it, which means that, of course, C is the hypotenuse, and that would be the hypotenuse no matter which of the angles you're using, 38 or 52. There's only one hypotenuse in the right triangle. So if I am using an adjacent and a hypotenuse, that would be the cosine. So again, using our SOHCAHTOA, we'll say this, cosine of, and I'm going to use again the 52-degree angle. Cosine is equal to adjacent, which is 35, over hypotenuse, which is C. Now, in order to solve for C here, which we'll have to do, that's our goal, we'll finish once we solve for C, we have to do a little bit of algebra, and there are a couple different ways we can do that. So in order not to create too much chaos and busy looking work, I'm going to use an efficient path to finding C, which is you can just cross multiply. If you think of cosine of 52 degrees being over 1, we have that on one side equal to 35 over C on the other. If we simply cross multiply that ratio, cross multiplying works when you have an equal sign between two fractions, okay? And in that case, we'll end up with C times the cosine of 52 degrees, that's one of the diagonals, equals, the other diagonal was 35 times 1, which of course is 35. Now remember, I'm trying to solve for C, and I currently have that on one side multiplied by this cosine of 52 degrees. So in order to get C by itself, I would need to divide by the cosine of 52 degrees, but of course we'll have to do that on both sides. Cosine of 52 degrees. Those cancel on the one side we started with, cosine over cosine cancels there, leaving us with only a C, which is of course what we wanted. Now, I'm going to write this down below where I have a little bit more space. So C by itself equals 35 over the cosine of 52 degrees. This is another calculator crunching step. So let's go ahead and pull out our calculator, this time to plug in that value. So as we did before, we have to make sure we're in degree mode. Of course, I just put it in that, so it should stay once you shift it. But just double check, make sure you're in degree mode by hitting the mode key. Once you are, we want to type this in pretty much as seen. So I'm going to type in 35 for the numerator, divided by, and then the denominator is cosine of 52 degrees. So I'm going to hit in cosine 52. Make sure to close parentheses. It's a good habit to have. Again, it's assuming we mean 52 degrees since we're in degree mode. Now I will hit enter to let it crunch, which turns out to be 56.84942359. All right, so we're obviously going to have to round that as well, and I'll just keep with the rounding to 2 decimal places like we did with the first one, which will give us approximately 56.85. All right, so let's go ahead and write this in, approximately 56.85. This represents C, which remember is a side length. And so I'll rewrite that over here. 56.85 equals C. That was one of the things we needed to find. So now we've found C, we found A, those were our 2 missing sides, and we found theta, that was our 1 missing angle. We have all the sides and all the angles, which means we have solved this right triangle. All right, let's go on to a next example. This next one says, find x rounded to 1 decimal place. Notice this time it specified the rounding. In the previous problem it did not, but we'll pay attention to those kinds of things. And in this case, there's a diagram. Now this one's a little bit busier, so I'm going to describe it here. It's a few triangles kind of put together. If you think of it this way, there's a large right triangle labeled A, B, and C as its vertices. If you think of that as a large right triangle, then its right angle is kind of sticking upward at the top, and its hypotenuse would be at the bottom, which actually is exactly where X is labeled. So in other words, we want to find the hypotenuse of the larger right triangle. However, there are a couple smaller right triangles that are kind of forced into this diagram by the following. If I drop a segment vertically from the top of the triangle, which is where point B is, all the way straight down, making a right angle with the opposite side, the hypotenuse, then that creates two smaller right triangles that are within our larger right triangle. Now, in order to make the communication of this a little bit easier, I'm going to label, put a couple extra labels in here. As already stated, the x that we're trying to find is basically the hypotenuse, which goes all the way from A in the bottom left corner all the way to C in the bottom right corner, those being vertices or corners of the biggest right triangle here. Now, what I'm going to do is label the point that, if you take the point B at the top and drop the segment straight down to forming a right angle, by the way, that's called an altitude if it forms a right angle like that, that point doesn't have a name in the diagram, but I'm going to give it a name just for convenience. I'm going to call that point D. You could call it anything else you'd like. It's just convenient to give it a name. Because what I'd like to do is take the entire x segment, that is the hypotenuse, kind of all the way across the bottom of our triangle here, and I'm going to give that two individual names. So from A to D on the left side, I'm going to call that x sub 1, or you can just say x1, just so I can visually know, okay, that's part of x, but it's only from A to D, of course D being that point we added in where the altitude drops from B straight above. Okay, and then the other side of D, from D to C, we're going to call that x2, or x subscript 2. Because then what we'll be able to find, I think, is if you know x sub 1 and you know x sub 2, then you simply add those together to get the full x length that we're trying to find. So it's just labeling for convenience of communication here, really. It would not be necessary to put those in, but I think seeing them there can help understand where I'm going with all this. Now, why might that matter or help to label those? Because, as noted, there are actually several right triangles in this picture, and we know how to work with right triangles. So right triangle ABD, which is the smaller one fitting within the largest right triangle, I'm going to star that so you can know what I'm talking about right there. That's triangle ABD, just kind of tracing the vertices is how you can label a triangle or name it. ABD, trace those and you'll get that right triangle. Of course, it has a right angle at D. That's where the altitude hits the bottom of the triangle. That's one of the right triangles we have to work with. The other one would be on the opposite side of it, and I'll give that 2 stars. It's a little bit larger of a right triangle. That would be triangle BDC, if you trace that way. Again, just using those labels. Now, what we can do is find x1 and x2, or x sub 1 and x sub 2, and then simply add those together. But we can find each of those using trig ratios since they are part of right triangles. So let's just do one at a time. For x sub 1, notice that's one side of a right triangle. Again, just a note, where point D is, you have right angles on both sides of it because it's an altitude that drops down, forming where that intersection is. So in other words, x sub 1 is a non-hypotenuse side of one of those right triangles. How do I know that? Because remember, across from the right angle would be the hypotenuse of that smaller right triangle. So we can label side AB as a hypotenuse of that smaller right triangle within our picture. Or similarly, we could label side BC as a hypotenuse. That's on the other right triangle, the bigger one that's within the largest one. But if we have those labeled, we can hopefully remember all of our trig ratios and use what we need and know to find something. We know the altitude is labeled as 100. Okay, we don't know the units, but it's some length of 100. Angle A is labeled as 60 degrees, and then angle C is labeled as 30 degrees. So with all that being said, we can go ahead and find, well, what we need. So let's do this one piece at a time. If I want to find x sub 1, that is segment AD, as I've labeled it. Notice that that is, you could say, the adjacent side for angle 60 in the smaller right triangle, which means I can use that as something I need to know, and I can use the opposite, that is the side length labeled 100, the altitude dropped from B to D, as part of a trig ratio. So think of this. Which trig ratio uses the opposite and the adjacent? Well, it's tangent. So we can say that tangent of 60 degrees would equal opposite, that's 100, over adjacent, that's x sub 1, as we've labeled them. That's just using a regular trig ratio for the smaller right triangle on the left side of our diagram here. But that's helpful because now I can solve for x sub 1 algebraically here. In fact, you could cross multiply, again putting tangent of 60 degrees over 1. And what we'd end up with is that x sub 1 times the tangent of 60 degrees, that's one of the diagonals, equals 1 times 100, or in other words 100, which means if I divided by tangent of 60 on both sides, I would end up with x sub 1 equals 100 divided by or over tangent of 60 degrees. Okay, why does that matter? Because x sub 1 is part of what we're trying to find, right? X sub 1 is part of x. So let's keep going to find x sub 2 in a similar kind of way. So I'll write it over here. We're using now the 30-degree angle. So this is now we're shifting over to the larger right triangle that's within our biggest diagram. On the right side here, we have an angle 30 degrees, which means we want to know the adjacent side to it. That's where x2 or x sub 2 is labeled. And we know the opposite side, which is still the 100. So this is another case of using an opposite and an adjacent together, which means we're going to go with tangent again. So we'll say tangent of our angle 30 degrees equals opposite, well, across or opposite from 30 degrees, that's where our 100 is. So there's opposite over adjacent, that's next, right next to the 30 degree, touching it would be x sub 2. So we have tangent of 30 degrees equals 100 over x sub 2. Well, again, if we put tangent of 30 over 1 and cross multiply, we end up with, let's see, x sub 2 times the tangent of 30 degrees, that's one diagonal, equals 1 times 100, that's the other diagonal, which means x sub 2 equals, if we divide by tangent of 30 on both sides, x sub 2 equals 100 divided by tangent of 30 degrees. Okay, so why does this matter? Well, if we were trying to find x, and x is really made up of two segments, let's label these here. So we have x sub 1 that we've already found, at least in its symbolic form. But then also it's x sub 2, which again we've already found in its symbolic form. Then if we simply put those two segments together, they will form x, which is ultimately what we're trying to find. So let's do that exactly. We'll write this out by saying x equals, okay, so x sub 1 is first, that's 100 over the tangent of 60 degrees plus, okay, so there was just the x sub 1, plus x sub 2, which is 100 over or divided by the tangent of 30 degrees. And so we have an expression representing x. It is 100 over the tangent of 60 plus 100 over the tangent of 30. All we got to do is approximate that by computing it on a calculator. I'm going to demonstrate typing this in. We just got to be careful with the fractions here. The first fraction in this answer is the 100 over the tangent of 60. Just to be extra careful, you could put parentheses, but the calculator will understand this simply by order of operation. So you could put 100 divided by tangent of 60, again, assuming or making sure we're in degree mode, it's 60 degrees. And then if I put a plus, the calculator will not require me to put that first fraction in parentheses, though you could. Plus the second fraction would be 100 divided by, and then it's tangent of 30 degrees, so tan 30. Notice closing the parentheses after the trig function inputs. If I hit enter now, it should follow order of operations correctly and spit out 230.9401077. Or since the instructions said to round to one decimal place, we'll just call that 230.9. So we'll go ahead and write that in, 230.9. Now that's a side length, but we don't have any units with it, so we don't know if it's feet, inches, miles, whatever. We're just going to leave it as a numerical value without a unit with it in that way. All right, let's do one more example in here on this topic. This next problem says this. A man is lying on the beach flying a kite. He holds the end of the kite string at ground level and estimates the angle of elevation, that sounds important, of the kite to be 50 degrees. If the string is 450 feet long, how high is the kite above the ground? Okay, this just begs for a diagram, doesn't it? Now, you don't have to be an artist. You just have to make sure things are labeled accurately. So let's draw the ground. We'll start with that. Just draw a nice horizontal looking segment to meet the ground. And we have the person holding the kite. Now remember it said he's holding it at the ground level. So let's just kind of assume that I'll draw a little point at the end of the segment where let's say he's holding the string and then the string is attached to the kite which is flying above. So I'll just draw an angle that's going upward toward the sky, of course, where you would find the kite. Let's draw a little kite up there flying above the sky. And then, of course, that kite has a certain elevation above the ground. I'm just going to draw in an altitude, which is a segment straight down to the ground, making a right angle with it to represent the height of that kite. Now, let's see if this all makes sense. Remember, angle of elevation means that according to the horizontal segment, which is in this case the ground, you would be then from the string kind of gazing your look upward or rotating your head upward. That would be where we could label theta perhaps as our angle. And that fits this diagram because then you have the kite string going upward from that all the way up to the kite. What we know, or what they say, is that he estimates the angle of elevation to be 50 degrees. So we're just going to write that in as 50 degrees. We'll assume that it is. What else we know is that the string is 450 feet long. So we'll label the string, the one going all the way up to the kite, as 450 feet. And then the question is, how high is the kite above the ground? Well, that's our missing side length, which we'll just call x, just to give it a name. As you can imagine, we have a right triangle, which means we can label some things, okay? So across from the right angle, we have the hypotenuse. Label it as that. If we're using the angle 50 degrees where theta is, then across from that angle, you have the opposite. All right, so we know the angle 50 degrees, we know the hypotenuse, the kite string 450, and we want to know the opposite, which represents the height of the kite, right? So all we got to do is pick a trig ratio that uses those, right? We're working with opposite and hypotenuse, so think through your SOHCAHTOA. Which one is it? That's right, it's sine of 50 degrees. Sine is opposite, which would be x in our case, over hypotenuse, which would be 450. So there's our trig equation we can use to solve for x. We can do so by multiplying both sides by 450, which is just algebra, in order to get the x alone. So the 450s cancel that are near the x there. We're left with x all by itself, and we'll likely have to round this. So let's say x is approximately whatever 450 times the sine of 50 degrees is. And we'll go ahead and pull out our calculator to figure this out. So again, making sure we're in degree mode, we're just going to type this in here, 450 sine of 50, assuming it means 50 degrees, close parentheses. Let's hit enter. Let it spit out a nasty looking number. We'll round it. This one did not say what to round to, so we'll just kind of pick on the 100th, again, just to be safe. A couple decimal places is good. And we'll call this 344.72. So approximately 344.72. Now this problem actually did give us some units, and so we'll go ahead and use that. This would be feet. That's what it was given in. Of course, you could round that to different places if asked to do so, but without any specific instruction, we'll just kind of give it a couple decimal places to work with, and there we have it.